circuits ones with Laplace transforms, changes them to the S domain where you can use all algebra. What you can do if they're all sinusoidal functions is use phasors. And then when you use phasors, and the same thing happens with the S domain, when you use phasors, then everything acts like a resistor. And what I mean by that is that you're going to change your inductors and capacitors to this phasor domain, and then you can treat them like resistors. Things in series add together, things in parallel you do product over sum. Unfortunately, of course, it's not super easy because it ends up being complex. And whoever figured this out was really very clever because Euler's identity says that e to the j omega, you can write it in terms of a sine and a cosine. And so we start using these complex numbers, even though the real world is not imaginary, the real world is real. But you take the real part of that, and then the algebra is a lot easier in the complex numbers than it is if you're just using the real numbers. And it may not seem that way, but I just kind of wanted to let y'all know that that's what's going on here, is we're really doing this to make things easier. And you just have to trust me that if we didn't do this, if we didn't change to the phasor domain, it would be really, really hard. Okay, so here's what we do. We have these equivalences. And so our equivalences are that when resistors are still resistors are always resistors. And so whatever the value of the resistor is stays the same. When you have an inductor, when we take that into the phasor domain, so if the L is the value of the inductance, then in the phasor domain, it's going to be j omega L, where omega is the frequency. And it's actually the angular frequency, although a lot of times we just call it the frequency, but you have to pay attention to the units to see which one we're talking about. So if we give a frequency and we say it's 10 hertz, then that's frequency F. That's F frequency, that's not angular frequency. If I say, and to get omega from F, omega equals 2 pi F. And so if F was 10 hertz, then omega would be 2 pi times 10, and that would be in radians per second. So if the frequency is given as in radians per second, you know they've given you omega. If it's given in hertz, you know they've given you F. And you need to pay attention to that because if you don't do that, then you'll get the wrong answer. Do you mind scanning the QR code real quick?
Yeah.
There we go.
I believe. Okay, it worked.
All right. Okay, so we'll take our inductance and it becomes j omega L. Oh. Do you mind scanning the QR code? Okay. And the capacitance, when you take the capacitance, it becomes 1 over j omega c. And that is the official transformation, but usually we write it another way, because if I multiply this by j over j, then the numerator becomes j, and the denominator would be j squared omega c, and j squared by definition is -1, so it's minus j over omega c. So even though officially a capacitor in the phasor domain is 1 over j omega c, and it's identical, we usually just skip straight to saying minus j over omega c, because that'll be easier to work with. Just like you learned last semester, in the phasor domain, if it was DC, then, and it had been DC, then an inductor acts like a short circuit and a capacitor acts like an open circuit, just like what you're used to. What's different is this high frequency equivalent. So if you have a very high frequency, then an inductor acts like an open circuit and a capacitor acts like a short circuit. And so if your frequency is very high, that's what you have. And your impedance, and I'll talk about impedance in a minute, what that means. The impedance depends on the frequency for your inductor and your capacitor. So for a resistor, I said a resistor, the resistance is always just the resistance. So the resistor is just constant. It doesn't matter what the frequency is. But if you have an inductor, it changes, it's proportional to the frequency. So as the frequency gets bigger, the impedance gets bigger for an inductor. And for a capacitor, it's equivalent to the absolute value 1 over omega c. So as the frequency gets bigger, the value of the impedance from the capacitor, which we're going to talk about, that's actually has another name. We'll get to that in a second. Okay, so that's how we're going to change things to put it into the phasor domain. So now what I would like to do is talk about what these terms are. And so we have these new terms that we're going to be using now in the phasor domain. Instead of just V equals IR, we've got these other things. So we have impedance. And so we are used to Ohm's law, V equals IR, and R equals V over I. So what is impedance? Impedance is Z. So it's the letter Z, and I usually put a little line in my Z's. And it is the voltage phasor over the current phasor. And it is generally, well, it is always a complex number, but remember, a complex number has a real part and an imaginary part. And the imaginary part or the real part could, either one of them could be 0. So these are complex numbers. I don't know why my pen is red. Okay, so if it is a complex number, then that means, Dr. Trahan, would you like me to shut the door? I guess he can't hear me. Okay. So if it's a complex number, that means we can write it like this. Z equals R plus JX. Now, if you weren't here, or if you haven't been paying attention in class, or if you just missed it, and you're like these last few weeks you've been, what is going on? J is the square root of -1. When you were in high school, you called it I. And engineers call it J, just to keep it separate from circuits. So J is the square root of -1, and J squared is -1. And so impedance has a real part, and it has an imaginary part. And so the real part of impedance, and it's actually a function, just like adding is a function or subtracting is a function. Taking the real part of a complex number is a function, and your calculators can do this. If you have that calculator right there, the TI-36X Pro, or probably the 84, definitely the 89, there'll be something that says real part. So the real part of the impedance is R, and that's called the resistance. And so that is just exactly what you're used to. By the way, impedance is measured in ohms, just like resistance was. And everything is measured in ohms. So when we say, when we change the inductor to J omega L, that's still going to be ohms. A capacitor 1 over J omega C, that's still going to be ohms. So everything's measured in ohms. Okay, now reactance is the imaginary part of the impedance. And that's X. And when X is greater than 0, we call that inductive impedance. And if you think about that, that makes sense because we said for an inductor, the impedance was J omega L. That the omega L is going to be greater than 0. And so the impedance that you get from an inductor, that part is, it's not positive because it's imaginary, but the omega L part is positive. And if X is less than 0, then we call that a capacitive impedance. And again, that makes sense because the impedance from a capacitor is minus J over omega C. And so that's negative. So when you get your final answer and you are asked whether it is inductive or capacitive, you'll look at the imaginary part. And if the imaginary part is negative, then it's capacitive, and if the imaginary part is positive, then it's inductive. Okay, so you might or might not remember that instead of using resistance, you can use conductance. And so back when y'all first learned about resistance and you said it was measured in ohms, you also might have, it was in your book, I don't know if y'all talked about it, you might have talked about something called conductance. So if the resistance of something is how much it resists the flow of electricity, if you take its reciprocal, it's how much it conducts electricity. And so conductance has the symbol G, and it has the unit Siemens, which it is what it is, okay? Okay, so, and just like all of our impedances are ohms, all of these reciprocal values are going to be measured in Siemens. So admittance is 1 over Z, and we call that Y. So if Z is impedance, 1 over Z is Y. Now, you can't just take 1 over the real part plus 1 over the imaginary part because it doesn't work that way. If I had 1 over 1 plus 3, that does not equal 1 over 1 plus 1 over 3. 1 over 1 plus 3 is 1/4, and 1 over 1 plus 1 over 3 is 1 1/3. So if I want to take, if I need to find the admittance, I have to take the reciprocal of the complex number, and then you have to do complex algebra on that. Now, the conductance is still G, just like over here, and it is the real part of the admittance. Now, that doesn't mean it's going to be 1 over the resistance. So you just have to keep that in mind. And the susceptance, which has the symbol B, is the imaginary part of the admittance. Now, the circuits textbook that we use for circuits 1 and circuits 2 doesn't use these that often, but there are some people who really like to use those instead of resistances. So you'll get into some classes where they use conductance, and you just have to say, okay, I'm going to switch my mind over to that, and I'm going to flip everything upside down. So just be aware of that will happen to you, that there's some people that like to use that. Okay, so any questions on anything before we start some problems that are like your homework, like your quiz, where you have to find, if I recall, your quiz was you were given a circuit and you had to find the impedance relative to 2 terminals. Did you have a question? Okay. So for those of you who came in before, I am recording this, but I'm not posting it. It's just in case I need to use it for something else. Or I said I was recording it. Yeah, am I